Study Unit 5, Lecture 2. This lecture continues where Lecture 1 left off, but instead focuses on single-phase, full-wave bridge rectifier circuits. These circuits are an extension of the half-wave rectifier, but instead of only half of the energy being used during the AC cycle, now all the energy is used during the entire AC cycle. So for the case of a half-wave rectifier, the output voltage, or as a function of omega t, is simply the output current multiplied by a resistor for a resistive load, and this was root 2V sine omega t, and this is for a half-wave rectifier. For the case of full-wave rectification, the absolute value of the sinusoidal generates the output current over the resistive load. So for the very basic case, only this part of the sinusoid was used to conduct, but in full-wave rectification, the second part of the sinusoid can also be used to conduct current through the load relative to 0 at the output. Calculating the average voltage at the output with full-wave rectification for a resistive load is simply the average of this first half cycle and the following half cycle, and that can be determined by taking the integral of the area underneath this function, and this results in an output voltage having an average value of 0.9 times the input voltage. So as expected, this is about double that of half-wave rectification. The power dissipated for a full-wave bridge rectifier is simply V squared over R. Figure 11.7 from the reference text shows such a full-wave rectifier. It consists of an AC source, a diode bridge, and this delivers current to a purely resistive load. And here is a repeat of the graph which I drew, which shows the load voltage as the source cycles. What's also indicated on this graph is when which diodes are conducting when. So in the positive part of the cycle, diodes D1 and D2 are cycling, so the current is flowing through the resistive load back through D2 and into the source. And in the second part of the cycle, the current flows through D3, through the resistor, and then back through D4, back into the source. As with the half-wave case, for the full-wave rectifier, the case of a load with a back EMF should also be considered. The derivation for the full-wave case is very similar to the half-wave case, in that the presence of the EMF source now changes or rather increases the amount of voltage required across each diode before the diode will conduct. What this effectively means is that the amount of time that each diode conducts during each half cycle is less, and the conduction time will be once again be between some angle alpha and some angle pi minus alpha. Once again, the output voltage is determined by the potential over the EMF source, as well as the current being converted to a voltage through the resistive element. So the output voltage now has a component due to the EMF plus a component due to the alternating sine wave through the resistor. So the output voltage is given by some DC offset 2e alpha over pi plus the expected periodic component of the converter. So the only real difference here with the half-wave case is that now there is an additional pulse of energy, or rather pulse of current, flowing through the resistor during the negative part of the AC cycle. So realistically, a purely resistive load is not always really realizable or practical, and most loads will have an inductive element in series with a resistive component. Two circuits are presented here in figure 11.8, circuit A and B. Circuit A has a transformer coupled source, so does circuit B, and both have a resistive and inductive load. The key difference is that circuit A requires 4 diodes for the full wave rectification, and circuit 2 only has 2 diodes. So 2 diodes can be done away with by making use of a center tap transformer, where the 2 secondary coils have 50% of the copper usage of the primary coil. These secondary coils need to have the same voltage rating as the primary, and also the 2 diodes which replace the 4 over here need to be able to withstand twice the voltage of the 4-way or the 4-diode full-wave rectifier. This is because these diodes will experience twice the voltage through each switching part of the cycle, or through each switching cycle. Despite being more complex, the behavior of these two circuits is actually simpler than for the half-wave case for an inductive load. The derivation of the output voltage is the same for a purely resistive load, and the output voltage average is simply 0.9 multiplied by the peak voltage of the AC source. The reason for this simplified behavior is because the average voltage across the inductor is 0. Going back to circuit B, the reason these simplifications can be made is that by using a center tap transformer, you are effectively creating two halfway rectifiers which are out of phase by pi degrees, or rather pi radians. So during the first half of the cycle, the first halfway rectifier will perform the rectification, and during the second half of the cycle, the second diode D3 will perform the rectification. So shown in part C of the diagram are the expected waveforms. So the voltage output has very much the same type of characteristic which is expected from a full wave rectifier. The current of the output has a sinusoidal characteristic about the average output current. Coming back to the form factor for the circuit, so if you want you can look at the derivation in the textbook, but the form factor for the full wave rectifier is 1.11, which is significantly better than the form factor for the half wave rectifier, which is 1.211. Recall the ripple factor for a circuit, which is a measure of the quality of the DC conversion, will be 0 for an ideal converter. So the closer the form factor is to 1, the closer the ripple factor will be to the ideal value. So shown here is once again a full wave rectifier with an LR load, and there is also an additional filter capacitor C which has been added in parallel across the load resistance. So for this circuit, the output voltage is given by the average output voltage plus a harmonic component, and what's often used in the text and for following derivations is only the second harmonic or the first two harmonic components are considered when determining the contribution of the harmonic components to the output voltage. So the output voltage is given by the average voltage 0.9 V plus the harmonic component 0.6 V cos 2 omega t. An important aspect when designing circuits like this is deciding on an inductor value such that there is continuous conduction throughout the entire conversion cycle. So the inductor current will be the same as the resistor current. There is no current through the capacitor. So the inductor current is given by the output voltage divided by the resistance plus the harmonic component divided by the impedance of the inductor and the resistive element. So for continuous conduction, the average current, I0, given by 0.9 V over R, needs to be greater than the harmonic contribution to the current through the inductor. So in other words, the average current needs to be larger than the harmonic contribution. Another way to write this is that the average current, which can also be expressed as the output voltage divided by the resistance, needs to be larger than the average output voltage divided by the impedance contribution of the second harmonic. If the load resistance is chosen to be small, then the output impedance Z2 will be approximately 2 omega L. Substituting this approximation back into this inequality here means that the L to R ratio just needs to be larger than 1 over 3 omega. What this shows is that the amount of conduction, or the conduction time during the conversion cycle, is not only a function of L and R, but also the switching frequency of the full wave rectifier. So the final circuit that's considered for this lecture is a full wave bridge rectifier, but instead of having an inductive resistive load, it has a purely resistive load with a filter capacitor over the terminals of the resistor. So as with all cases where there is a reactive element with the load, there will be some angle alpha and some angle beta through which there is conduction from the AC source to the resistive load. The advantage of this circuit is that the capacitor does a fairly good job of suppressing the ripple voltage at the output, and is also fairly cheap to manufacture. The disadvantage is that the input current has very high peak RMS values, and the power factor of the circuit is also quite poor. So how does the circuit work? Assume that there is some voltage across a capacitor C. If this voltage is lower than the voltage coming from the source supply, then diode, for example diode D1, will turn on and start to conduct, and current will flow. This current supplies current both to the load and also charges up this capacitor. As the capacitor charges up, the voltage across the terminals of the capacitor will also increase. What this means is that the voltage at this node of the diode will also increase, and eventually the diode will turn off as the voltage across the capacitor approaches the voltage from the source. It's at this point beta that no conduction takes place from the source through the diode to the load. Instead, current to the load is now provided by the energy stored in the capacitive element. As current is drained from the capacitor, the voltage across the capacitor will also fall, and eventually this will fall to some value which is lower than the voltage present from the AC source, and one of the diodes will turn on again, and then conduction will start again, and the process will start all over again. Because of this behavior, there are two components when considering the currents and voltages in the circuit. The first is the AC component from the AC source as it conducts through the diodes, and the second is the exponential decay as current is sourced from the capacitor to the load. This rate of decay is determined by the value of the capacitor and the load resistance, as well as the frequency at which the AC source is switching. The reference text has a fairly detailed breakdown of what is happening here mathematically, and is strongly recommended that the student just reads through this to gain understanding of the mathematics which define this very simple looking curve. Finally, what's shown here is that the period of conduction through diodes are quite short, which results in very high energies being present in these current pulses during the switching cycle. And that's it. That's sort of a brief overview of single phase, half and full wave rectifiers. The remaining lectures in this study unit will look at three-phase circuits as well as DC multiplication circuits.